Hello everyone, and welcome back. Over the last couple of lectures we've been talking about work and how that relates to different kinds of energy, kinetic energy, potential energy. What we're going to do now is start taking a look at a new area, which brings us to section 8, conservation of linear momentum. And I'd like to start out by thinking about what kinds of things have we been talking about. When we have been looking at the motions of objects, we have basically been ignoring any of the structure of the object itself. So for example, if we were looking at a person maybe running or something like that, we weren't thinking about the structure of the person. You know, where were their arms and legs, or were they sideways or upside down, or what? We basically assumed that we could describe their position as a single coordinate, one value of x, or maybe x, y, z, or something like that. What we want to do now is start taking a little bit more, or start looking at things in a little more detail, trying to understand how might we describe a larger object. Single, very small things that can be described as basically a single point, we call particles. And so far we've been describing everything basically as a particle, no matter how big it was. And that's fine under certain circumstances. Sometimes you could describe an entire galaxy as a single particle if you didn't need to worry about the structure of the galaxy or something like that. You just want to talk about where is it, how is it moving, something like that. Well, let's start thinking about this. How can we actually describe things a little bit more complicated, in a little bit more detail? Well, what we're going to do is, rather than talk about things as a single particle, we'll start with two particles. That'll at least make it a little bit more complicated, and we'll see where we can go from there and generalize things as much as we want. Let's start with two particles, two masses. And let's imagine that they are on, let's say, just in one dimension, on the x-axis, say, for example. Let's imagine we've got one mass of, say, m1, another mass, another particle, say a mass of m2, and let's say this one is at a position x1, and this one is at a position x2. One thing that is going to be important is to try and figure out, well, where's the center of this system? Well, when we're talking about more than one particle, we'll refer to it as a system, regardless of what it is, a person, a car, a ball, or a galaxy, or whatever. That's the system that we're talking about. So where is the center of our system? Where's the center? The center will be kind of a good general point that we can use to describe where the object is. So where is it? Well, we might think if these two masses were the same, if they were equal masses, the center of this system should be somewhere right in the middle, right in between them. Perhaps we might say the average of x1 and x2, and that would be fine. But what if one of them were much bigger? If m1 were much larger than m2, we would imagine that kind of pulls the center over closer to m1. The center in that case of the system we would expect to be closer to m1, closer to x1 than it is to the value of x2. And if m2 was much larger than m1, we would expect the center to be somewhere over here, closer to the value of x2 than to x1. So how are we going to define this? Well, we're going to define a very important quantity that's called the center of mass. I'm going to put down a definition for the center of mass, starting with just two masses, and then we'll generalize that. We'll look at some examples and see why it gives us results that make sense. But if you want to get a better idea of where did this definition come from, why do we use this definition, I wrote up some extra notes on the meaning of the center of mass. Please take a look at those. And if I get a chance, I will make a video of those, going over those notes as well. But for now, let's just accept this definition. What we're going to do is we're going to say that the x value of the center of mass, so this means the coordinate value of the center of mass, cm, short for center of mass, we will make this definition is equal to m1 times the coordinate value of m1, which is x1, plus m2 times the coordinate value of x2, and then divided by the total mass, where, let me emphasize, the total mass is m1 plus m2. All right, so that's what we're going to use for our definition for now for the center of mass of two objects. Remember, 2-point masses, one with a mass of m1 at a point x1, the other with a mass m2 at a point x2. Let's just stick some numbers in here and see how that works. Let me redraw our little diagram that I had before. Here's our x-axis. Let's imagine at a point of x equals 2 meters, so we'll call this x1. We have a mass of 1 kilogram. We can make this 3 sig figs if we want. And let's say at 6 meters, so that's 2, 3, 4, 5, 6, so at x2 equals 6 meters, we have a mass of, let's say, 3 kilograms. Let's figure out what this gives us for the center of mass. We get the x position of the center of mass is equal to m1, so that's 1 kilogram, times x1, which is 2 meters, plus m2, which is 3 kilograms, times x2, which is 6 meters, divided by the total mass, which is 1 kilogram plus 3 kilograms, or 4 kilograms. All right, so what does this give us? Well, 1 times 2 is 2, 3 times 6 is 18, 2 plus 18 is 20. So in the numerator, we're going to have 20 kilogram meters, so kilograms times meters, divided by 4 kilograms. 20 divided by 4 is 5. And the kilograms cancel, and we get meters. So, the position of the center of mass is at 5 meters. Let's see if that makes sense. So 5 meters, we've got, here's 2, 3, 4, 5. So here is the center of mass. Well, notice, what did we see? What did we say? We said that if one of the masses were larger than the other, that would pull the center of the mass over. Well, notice the 3 kilogram mass is larger than the 1 kilogram mass, and the center of mass is not at the midpoint, it is now closer to the 3 kilogram mass. Okay, so that makes sense. That agrees with what we thought. But also notice, the distance from the center of mass to the 1 kilogram mass is 3 meters, while the distance from the center of mass to the 3 kilogram mass is 1 meter. In other words, m2 is 3 times as large as m1, but the distance to m1 is 3 times as large as the distance to m2. In other words, the larger the mass, the closer the center of mass is to it. Okay, that's a very, very interesting result. Great. Let's go back to our definition and see what we can do with that. Here is our initial definition. I'm just going to rewrite this slightly. I'm going to multiply both sides by the total mass. And what do we get? We get the total mass times the position of the center of mass is equal to m1 x1 plus m2 x2. Well, that's kind of interesting. What we have is a mass times a position on this side, mass times positions on this side, where here it's the total mass and kind of like the position of the entire object, so to speak, the center of the object, the center of mass. So mass times the position. While over here, we've got the mass of each tiny object, each particle or smaller object, times its position, and then we sum up all of those. Well, what if we had more than 2 particles? Well, you could just imagine that this would be plus m3x3 plus m4x4 plus m5x5, etc., etc. So we would just add these plus mass times positions, or we could write this as the total mass times the position of the center of mass along the x-axis is the sum of all the individual masses times their individual positions. And we can see pretty easily, we can extend this to multiple dimensions. We could say the total mass times the position of the center of mass along the y-axis, or the y-coordinate, would be the sum of the masses times the individual y-coordinates. And the total mass times the center of mass along the z-axis is the sum of all the individual masses times the z-coordinates. Okay, well that's very good. That generalizes it to as many masses as we want, as many point masses or particles as we want. We still don't have something that would describe a continuous object or a more extended object. But let's try using these. Let's stick some numbers in. Let's try at least a two-dimensional problem and see how we would solve that, and then think about how might we extend this to a continuous object. Let's imagine we've got 4 point masses, each one 1 kilogram, and let's say they form the corners of a square. We've got one at the origin. Let's say this is the xy plane. One is at the origin, one is at the point 1 meter 0, one is at the point 0, 1 meter, and then one is at the point 1 meter, 1 meter. So let's figure out what's the position of the center of mass. You might be able to guess what it is, but let's see if it actually works out given our definitions here. So what do we have? We've got m, the total mass. Well, what's the total mass? Well, we've got 4 1 kilogram masses, so the total mass will be 4 kilograms, times the x value of the center of mass is equal to, all right, m1 times x1. So we're going to go around. We'll start here, 1, 2, 3, 4. So we've got 1 kilogram times x1, and so we'll call this 1, 2, 3, 4. So what is x1? Well, it's at the origin, so x1 is 0, so that doesn't give us anything. We'll have 1 kilogram times 0. Then x2 is 1 meter, so we'll have 1 kilogram times x2, which is 1 meter. Okay. Then x3 is also 1 meter, so we'll have 1 kilogram. 1 kilogram times 1 meter. Okay, that's the mass, up here, mass times x. And then x4, what is x4? Well, mass 4 is on the y-axis, so x4 will be 0 again. So what do we have? We've got x center of mass equals 1 times 1 plus 1 times 1, that's 2. 2 divided by 4 kilograms is going to be 1/2, or 0.5. Kilogram cancels kilogram, and we get meters. So x center of mass is 0.5 meters. What about y center of mass? We've got total mass, 4 kilograms, times y center of mass equals y1, well, it's at the origin, so again, y1 is 0. y2, well, it's on the x-axis, so y2 is 0. y3, well, that's going to be 1 meter, so we'll have 1 kilogram times 1 meter, plus y4. y4 is again 1 meter, so we'll have 1 kilogram times 1 meter. Again, 1 times 1 plus 1 times 1 is 2. Divided by 4 is 1/2. YCM equals, again, 0.500 meters. In other words, the center of mass is at the point 0.5 meters, 0.5 meters, which is right here. Well, right in the center of the square. Well, the square, the 4 masses that are at the corners of the square, well, that makes sense. We probably could have guessed that. So it's good that when we have a simple situation, our definitions give us what we would guess. So that's good. Very, very good. What about kind of writing this in vector form? Can we do that? Well, yeah. We could take the first equation and multiply by an x hat. Second equation, multiply by a y hat. Add these two together, we'll have the total mass times x center of mass, x hat, y center of mass, y hat. Well, that's just the vector position of the center of mass, especially if we put down the z component. So we can actually write this as m times the vector position of the center of mass. And then what is this? xi, x hat, plus yi, y hat. Well, that will be the vector position of the ith mass. Add them all together. What's this going to give us? The sum of mi ri. And there we have a very nice vector result for as many masses as we want and treated in all three coordinates. So we can solve this. If it's a three-dimensional problem, we'll have three-dimensional vectors here and give rise to a three-dimensional vector for the center of mass. Very, very good. Okay. What if we have something that's more complicated, not just a point mass like, a little ball or something like that? What if we have a more extended object, something of some random shape? How can we use this idea to define a center or a center of mass for some extended object? Well, it's actually a pretty straightforward extension.